All right, we're going to start with a loop of charge. And we're going to apply the rule we talked about yesterday, Biot-Savart, to the loop of charge. So a loop of charge. I'm sorry, not a loop of charge, a current loop. So I said loop of charge. I'm just loopy. A current loop. So a current loop, meaning that there is a current passing through the wire. I hope that this goes without saying, but before I get the questions that I don't want to have today, I'm not going to go into what's generating this current. I'm not going to draw in a little tiny potential difference and a little fake resistor so that you can have your question satisfied about, well, where'd the current come from? Can we just all establish that if I have a wire, I could just put part of it in a loop and it'd be okay? So that those kind of questions can be left away for now. So I don't care where the current is coming from or how. I have charges that are just going in a circle in this wire, and that I have a measured value that says that the current in that loop is I. Is that all right? I gave you information yesterday, and I'm not sure that it's settled with you, but there's a magnetic field in the center of this loop. Is it out of the board or into the board? We're going to focus on the center, but you should be able to tell me the answer to this with the technique I gave you yesterday. Using the curl rule suggests that the magnetic field will be out of the board on this side of the wire, and that will be true all around this wire. But will also be into the board on the outside of the wire. Because we were talking about the fact that it's a circular magnetic field around the outside of this wire. Maybe I drew those arrows wrong. That way and that way. Now, this point in the center, we'll call it just point P for now. We are interested in the magnetic field produced there. I think we'll establish that we are in the center of the current loop. So this is, I'll say R, the radius of the loop. Biot-Savart allows us to break our current into multiple pieces and then add up all the pieces to establish the total amount of magnetic field. So many things to think about here. We need to kind of identify how all of these variables are related to a ds on our current loop. So I'm going to kind of give you a set of questions that I think are good for you to try and answer before you get started. For example, the first question is, how are ds, r hat, r, and I related? What relationships exist here? So let's answer that question first. How is ds, r, I, and r hat, how are they all related in this problem? Let's pick a ds. Pick my ds to be right here. ds has got a direction that is tangent to the circle, so that's the direction of ds. R hat is pointed towards the center because we're pointing towards P. R is going to be that distance between ds and the center because we're asking about the center. And I is the same everywhere on the loop. So a couple things that I'll just write out. I is a constant. Every piece of ds has the same current passing through it. R in Biot-Savart is actually a constant too. Every piece of wire is the same distance away. You guys follow that all right? Now, we only really need to worry about R hat in conjunction with ds, meaning how does this change for every ds? Well, in this case, it's the same. This is always going to produce a sine of 90 degrees because for every ds, we have a perpendicular between ds and r hat.
R hat is the direction?
Because r hat just contains the direction from ds to our point in space. So the first thing I think we should do after we kind of come up with that is recognize that we could probably manipulate this a little bit now with the information that we have. So let's do so. I can rewrite this to contain how my variables are related. How fun. What the heck happens on this campus half the time? All right, so next. This question seems obvious to me, but it's always less obvious to you guys. How can you point at each ds? I need a way to do so. So I need to find how to point to each ds. Yes, sir.
The angle, like the origin, so
All right, so I could pick a reference point and use the angle to point to each ds. You guys follow what he just said? I think that's not unreasonable. So I could pick a point, say here. And if I made that 0 degrees, I'd have to go out a certain distance for each one of them too, right? So I'd have to go out a distance, capital R, but could tell at which angle. So I'd turn a certain angle and go out, that's one ds, and turn another angle, go out, that's another ds. Does that make sense? All right, I think that would work fine. Jeremy?
You don't really, in this specific case, you don't need to because the integral of ds, since everything else is constant, is just going to end up being the circumference of the circle.
Well, that's probably true. Is it plausible, though, that in a circumstance like this, we might be using this as a metaphor for other circumstances where you may not have that kind of relationship? Okay. So I do think you're right. We could probably just sum this up in terms of the circumference. I think you're absolutely right. But I'm trying to stay away from the product that we get from the calculus and talk about the building of the integral, because I find that to be what generally is more troubling for folks. Is that not unreasonable? But you're correct. Yeah.
Well, if you know that the origin is just a pattern that repeats, so that you can follow that.
I think you probably can. I think that's also not unreasonable. So we've identified, though, a way that we can point to each ds. But that does change how we are going to structure ds. Instead of using ds, since we're going to be pointing to each ds by indicating the angle in which it acts, then it might not be a bad idea to rewrite it as r d theta, because the size of ds should be rewritten now in terms of how we point at each ds. Yes, we could do what Jeremy suggests and say, since all of them contribute the same, just add it up and not care about the shape. I'd like to maintain that there might be a reason why we should do it this way and take the long way around the road. What we're saying here is that I want to work into my integral a way of not only pointing to everyone, but figuring out the size of ds in terms of the way I'm going to point to each piece. So that's what we do next. And I'm going to rewrite this yet again to to incorporate that, now, we want the entire magnetic field that is produced by this single loop of current. I think that the last question that needs to be answered is, can you identify where the first piece is and identify where the last piece is? And does your manner of pointing at every piece contain every piece of the loop? Meaning, if we pick a starting point and an ending point, will our sum automatically add up all the individual pieces of the loop? I think it will. I think if we state that we're going to start at 0 and add up every single, let's try it again, add up every single piece from 0 to 2 pi, we will accomplish the task of getting every single contribution to the magnetic field. Of course, we have to add up every bit of those magnetic fields too. Yes, Oliver.
Could you also find find the integral from 0 to, I think it's pi over 2, multiply that by 4?
Sure, as long as it's symmetrical, yes. So, I think we're ready to execute this. And I know for a lot of you, getting here is the hard part. But I do want to point out, for the magnetic fields, we don't have the same kind of trouble on the exam as we do for electric fields. Meaning, there's just not many options. It's a loop, or it's a straight wire. You're going to see different stuff in your homework, but it's all variations on a straight wire and a loop. Everything that's a constant should be pulled out from your integral, which is almost everything that's here. We're going to have a mu naught for sure, I. Sine of 90 is 1, so I'm just going to ignore it. One of the r's cancels with one of those r's. So bring out the 4 pi, bring out the r, and what I'm left with is the integral of d theta from 0 to 2 pi. So as complicated as it looks, this one's pretty simple. Now all that's left for us to do is to do the integration. And again, I know you guys who are now in AB, you are in the throes of being excellent people to do antiderivatives and integration and all that garbage. So I don't feel like I have to do all the little stuff anymore. So I think we are kind of done in that will be the result of our integration. And now the magnetic field from a single current loop. Obviously, you should be prepared for a situation in which you have multiple loops. This is a way to make a magnetic field, a loop of current. We good to go? Pretty straightforward? All right. Not terrible. Not terrible. So let's...
Okay, the density of the magnetic field at the origin of that loop, or is it all of that?
No. This is just at the very center of the loop. It is not uniform inside that loop. You guys hear that okay? In fact, if I asked you to figure out the magnetic field here, I think that would be far more difficult. I'm not saying you couldn't do it. In fact, some of you who are jumping to the end, try it. You understand the way polar notation works, and you often have a propensity to want to jump ahead or correct me. Try this one.
It matters how close you are to the center, right?
It will matter how close you are to the center. There should be nothing wrong with you trying this out. Especially you guys who know polar projections. You can still treat this like a piece of arc. You can find the arc length in a similar manner. The difference is that for this one, every angle has a different r. You'll have to find a relationship between r and theta. But there is one. And you guys who have had any polar mathematics understand that. So try it out. Yeah. And no, I don't want you to ask. Let's try the next one. Not a huge extension here, but let's consider it a long line of current. Yes, sir.
Did you calculate the
Do it. You guys are smart. A few weeks we'll have a big honors breakfast to celebrate how incredibly smart you are. And you guys will be all smug about it and come up with your balloons, and it'll be fun, you know. So try it out. I'm not sure I could do it. I'm certainly not going to be put under duress to try and do it in front of you guys. I want to find the magnetic field here. And we should ask first, if the current is in this direction, should I put a dot there? Or should I put a cross there? What direction is the magnetic field at that location? Is it into the board or out of the board?
into the board?
You should be able to identify a DS here and a DS over here and verify using this right-hand rule that it's the same everywhere along this wire. You should try it. But we should also know that the curl rule works great. Put your thumb in the direction of the current. Your fingers curl in the direction of that magnetic field. So that's got to be it right there. It's got to be into the board at that point. Be honest, you need an explanation. I'm willing to try. Alrighty. Excellent. So I gave appropriate wait time. So into the board at this point, point P. We're looking for the magnetic field. Let's go ahead and make some kind of standard values here. I'm going to call this distance Z. I need to find a DS, so I'm going to use that DS. From there, I'd say that that's our distance from point P to DS. And dr r hat. R hat would be that arrow there. And the direction of ds that way. And that means that I wrote DS in a very inconvenient location. So I write DS on the other side. Boy, that I is in a very inconvenient location for me too. I don't know what you were thinking, Mr. Shelton. You should be better than this, but you're clearly not. So there. I'm doing all that because I want to realize that has to be the angle that we use for our cross product. So the angle for our cross product, and this one would be pi minus that angle. Just want to throw that in there. Okay. Obviously, this distance is going to come to matter, isn't it? Wouldn't you agree that that's going to be a distance that's going to come to matter? I guess I could call that S or X. I could just call it S right now, and that should be fine. But S is generally reserved for arc lengths. And so it's not particularly archy. So I don't know whether I should leave that out. We just need we need a placekeeper here. Something that tracks where every one of these is. So how about I just leave it as S, okay? Because that is clearly a piece in the direction of S. And that way I can just leave my other variables. Now, this should all look very familiar to you from the stuff that we did first semester in dealing with electric fields. We always tended to define all these things. One major difference, and this is worth noting, so I'm going to try and encourage you to pay attention here. All of the pieces of current contribute to a magnetic field in the same direction. This was not true for electric fields. For electric fields, every one of these pieces of charge created an electric field at this point that was in a different direction. We use symmetry to iron all that out. But we don't have to do that now. Every single piece of current is causing a magnetic field that is in the same direction here. So I'm not going to have to worry about that vector portion, since the vector portion is the same for all of them. In fact, let's start talking about the things that are related here. We have to see how is I, ds, s, r hat, r, and z. How are they all related? We're eventually going to have to get anything that's related all into the same variable. For example, every time I change s, I have a new r. Do you guys agree with that? So let's go ahead and get r, because we know our equation. Let's throw this up here again. Every piece of magnetic field, which I want to add them all up, has some constant out in front. Let's not forget about the stupid constant. And then we have our I ds cross r hat, all divided by r squared. Every single ds has a different value of s, and therefore a different value of r, and therefore a different cross product. All of these are related. We need to figure out a relationship. I think there's an obvious place to start. R is equal to the square root of s squared plus z squared. Right? Simple Pythagorean theorem. We're going to have to deal with that cross product because we know that ds cross r hat is going to produce sine phi. Right? Well, is it clear to you that sine phi is also equal to sine pi minus phi? That the sign of the supplement of the angle is the same as the angle? Sine is both positive in first and second quadrant. I mean, there's a lot of ways for me to say this, but would you agree with that statement? Do you need more help with that statement? We all cool with that statement then? So, what's that?
It's pi? I thought it was like a t.
I thought it made a... Okay, it could be a t. So let's make it a pi. Is that more pi, less te? All right. I live but to serve. So I'm thinking this triangle, right angle here, sine of that angle is going to be z over r. And therefore, z over the square root of s squared plus z squared. That all cool? All righty. I think we do be making some progress. So what do you think is left for us? Yes, sir.
are we using B on the outside? I was kind of confused about that. I've been spending the past like 10 minutes trying to think about that.
For all the audience members at home who are watching with just on bated breath, the cross product has been asked of us. What is it? How do we deal with it? So if I have vector A, length A, and in that direction, and vector B that way, and there's an angle between them that way, the cross product is A times B times the sine of the angle between them. For us, A is ds, and B is r hat. So I made a placeholder for the angle between them. And that means I have ds cross r, which has got to be ds times r times the sine of the angle between them. Moreover, r, by definition, should be written as r hat with the bars around it, because in this case, we are stripping away the directional information and writing just the magnitude. But the magnitude of r is 1. So that's my answer. Are we okay?
Okay, got it. The main thing I was confused about is I get the part now because I just didn't understand the vectors when we were basing the angle off of. I don't know why I didn't realize that before.
It's okay. I just want to be clear, and I'm trying to be compassionate and patient. Having a very zen moment today. All right. So I think we've done a lot to assemble this. What do you guys all think? Do you think we've done a lot to assemble this? I think so. I think we can begin to put some things together. I guess we can start by just doing some substitution in here. I think I'd give us a good place to begin. So dB equals, and we have come up with a way to point to each one, so I didn't ask that question again. But I still have to kind of put all the pieces together. I'm going to have an I here for sure. I'm going to have a ds here for sure. Taking away its vector bar because we're dealing with the cross product as we speak. That's going to be ds times the sine of phi all over r squared, which we have found to be s squared plus z squared. Are we good? Any questions? All righty. The next step, of course, would be to do that substitution. And then we have to choose a beginning point and an end point. And we're gonna integrate to infinity. If it were me, I would start at 0 and go to positive infinity and double our answer for the negative side. If it were me. You should try it at home. I will try and finish the video and post the rest of it, but you should try it at home. Assemble this integral, that's what we were talking about doing. We're going to replace the sine phi with our expression for sine phi, which will give us, and I'm sure you are way past me because you are very, very advanced. And, oh wait, I'm sorry, we didn't handle this. The last thing I want to do is ruin your flow. Am I allowed to say that in public school? I think so, right? That was okay? I am And I am carefully talking about people without saying names.
Spicy food.
So, we'll start with mu naught over 4 pi, and then we'll move on from there. I'm going to replace, I'm going to leave ds, but I'm going to replace sine phi with our expression for sine phi, which is going to still give us this ds term here and our s squared plus z squared here, and then z over the square root of s squared plus z squared. Now, we wish to identify, and I tried to break this up into parts yesterday. I don't know how successful I was. That first thing we needed to do was find out how all the variables are related. Second thing we needed to do was kind of pick a variable and go with that one. We went with s, if you'll recall. That was the one that we converted everything in terms of s, so that everything else was a constant. I said that you should be considerate of where your first and your last piece is. Our first piece is here. If you understand what I mean by that is, that's the closest point to where point P is that perpendicular distance away. So if we make that our first point, if we make this 0 on a number line, then we need to add up every piece from negative infinity to positive infinity. Now, that usually doesn't go well because of issues with parity. So one of the better ways to do this, and we've talked about this before, is to break your summation, if it's symmetrical, in half, and then just double your output. And that's a very reasonable thing to do here. So I think that we will, to get the entire magnetic field, we will add up all of the pieces, starting from what we have just described as 0, and go in one direction towards infinity, and then take this whole thing and multiply by 2 to ensure that we get the full sum of every contribution to the magnetic field. Fair enough? Now, mathletes, start your pencils. I don't want to say start your... The whole thing with mathletes. And I support mathletics. I even sent an email on the topic to the Mu Alpha Theta sponsor. I support mathletics because they have an event, I think tomorrow, where they will go and kick math all over the place. Right? Is that what you guys say to each other?
Yes.
So a lot of this has nothing to do with S, right? We've tried to remove any other variable that might be related to S. So anything that is not related to S, we should go ahead and immediately pull out in front of our integral. And that is almost everything. And what we're left with is this. Now, a few of you, probably not all of you, understand why this is a bit of a dilemma. If you don't, all of you BCers and all of you people who have finished BC, have at it. You guys in AB are not prepared for this integral. I'm actually of a mind that many of you who are in BC are probably not prepared for this integral. We've seen this before. It's been a while, but we've seen it before. It's missing something that would make its execution relatively simple. In that, if you were going to use, say, U sub, which is probably the most likely thing you would use, your U sub will fail in that you don't have what you need to cancel out correctly in the execution of the U sub. I mean, if you decide that U is going to be, say, z squared plus s squared, when you go du and you have z squared plus 2s ds, and you go to make this substitution, you understand why this U sub is going to fail. Because to do U sub correctly, you guys remember, your goal is to do the substitution here, so we'd get... And guys, if you haven't done this before, just chill. This is not going to be ever asked on a test for this class. I'm pointing out something important, I hope. And before you ask me questions, just give me a moment, perhaps. Part of the way in which you do U-sub is we're going to ignore this during the U-sub. And we decide on something that we would make for our substitution. And the most likely thing I think your brains would go to would be this, which would give me u to the 3/2 power. But I have to replace ds with du, which is why we take the integral here. We take the derivative here with respect to s to get an expression for ds, which, if you look, is going to be 1 over z squared plus 2s du. I'm sorry. The derivative of z squared is a constant. It goes away. So I'm letting myself be distracted, and I shouldn't be. I should just look at my notes. But so here we get 2s, 1 over 2s du. We sub that in, 1 over 2s, and that's a failure of u-sub. U-sub only works if, when you do your u substitution, you're left with a function that only has u in it. S is related to u, so we can't do this. Now, what you guys in BC understand that the folks in AB don't, and all of you who have completed calculus understand, is that once you learn the basics of differentiation and integration, you spend the remainder of the class trying to figure out all the integrals that don't meet the criteria for what you've learned. That is the basis for the rest of the class. The choice that could have made it so we didn't get stuck like we are here was a choice we made way back here when we decided that we were going to do the entire problem in terms of s. We didn't have to. There are other variables we could have chosen to use here. For example, we could have done the whole thing in terms of the angle. That would work. I mean, the angle goes from 90 degrees to 0, right? There's a way to do this. We could treat each one of these as an arc length based on that. This would transform the function into a trigonometric integral. It's not an easy one. I'm not going to say it's easy. It's not. But it would transform it into a trigonometric integral, which you probably would have the tools to complete. And I say still, probably. It's not easy. So I bring all this up because this is it. This is all the physics could do for you. It's it. The worst part is that even though this is all the physics can do for you, the answer actually is that this integral turns all of this into the number 1. I don't need to prove it to you. I'm not going to. If you want it proved to you at a later date when I'm not, under threat of you guys calling out all the mistakes I'm going to make. I'm sorry, I said that wrong. It's not turning into 1. It's a little different than 1. It turns into something similar to 1. The answer ends up being that's what the answer ends up being. Now, first, the answer ends up being a lot simpler than what it's going to take to get there. And I said to you yesterday, be careful. I'm going to say to memorize some stuff. There's a lot of reasons why I think you should commit this to memory. Now, for those of you who can't see it, because I have it tucked away in the bottom right-hand corner of the board, and I've got stuff stacked here to make sure you can't see it. I'll happily just do this. So, do you remember the magnetic field for the current loop from yesterday? Look at it.
N u naught I over 2r.
The n is for a number of loops. I'm leaving it out. And if I replaced the z with an r to represent the distance away from the wire, oh, why did I do that? I don't know. I'm just not thinking. You see, You see it, right? You see why this is kind of a pain? The one that's a circle doesn't have a pi in it, and the one that's a straight line has a pi in it. Is it because? I don't know. It's because. No, don't try and come up with some rational reason for it. It's because of math. We integrated in a circle and got a pi in the numerator and canceled out the pi in the denominator. And yes, it's because of nature in that all of our fields are circularly based and all end up with that 4 pi in the denominator anyways. However, commit these two things to memory, please. R represents the radius of the current loop in the top one. R in the bottom one represents a perpendicular distance from the wire. Okay? Commit it to memory. You will use it a lot. You'll use it a lot for the rest of this quarter and most of the next quarter. Wire loops of current and long wires with current in them show up a lot. This, yeah, you should look it up. I would recommend you do a transpose this into an angle if you want to work it out and show how brilliant you are. I am not interested in how brilliant you are. And I don't mean that mean. I just mean that I'm not interested. Some people can do it, some people can't. It's not important. I will say with a certain amount of... And I wish I had gotten here back from SJ just a little bit earlier because I was going to have it already written in here so I could have this surprise, but it just didn't work out. So the closest integral to this that we would have to use on my integral table is... Hold on, my eyes are old. All right, so that's the closest one I could find. And that would do it, right? If there's an integral table with this, that would work out. The difference is A is Z and is expressly negative in the function, but that's not a big deal. And X is S, right? N is 3. All good? I love this. I just love it. All right. Start your engines here. So even having the integral table, I gotta make sure I keep writing the right one. I already screwed up. My God, I shouldn't be holding this. See, this is why I'd hoped to do it before you came in here, so I don't screw it up. I screwed it up already. Here we go. This is... damn it, Shelton. 2 minus n there. 2 minus n times a squared here. Minus n minus 3 over n minus 2 a squared times the integral of a slightly simplified function that relates the same things. All right, so that's in the integral table. Now, of course, you do understand that I now have to look up this on the integral table, right? Or repeat this for n equals 1. Now this appears on the integral table though, so I can do this. This is just the one, but I have to go find that one. That is on the integral table. Just a moment. Where are you? Don't be so elusive, Mr. Integral Table. Here we go. The integral of dx over the square root of a squared plus x squared. Right? That's good, right? Because this was n equaled 3. We are subtracting 2 from it. So now this is n equals 1. So that's that, right? Okay, so I have 2 ways to express this. I'm going to express it in the simpler version because I use hyperbolic sign for one of them. And if you don't know hyperbolic sign, then it's not important. So, I want to say that, yes, you should try it. Do I want to prove that all that's just going to boil down to 1 over z squared? No, I don't. But you should. All you people who raised your hand and said, I have a certain satisfaction in seeing it done to the end. If you do this in trig, it's actually easier. Trig is easier. It's not easy. I didn't say easy. Easier. So I'm not throwing down gauntlet. I also think that you'd get a lot out of Wolfram Alpha's explanation of this integral. But now you're asking yourself, well, Mr. Sheldon, why did you tear us down this road to take us to a place that we can't do it? As I tried to say to you before, what's the point? Why do we teach Biot-Savart? Well, we teach Biot-Savart, spelled without an E at the end, because it is an expression of where this magnetic field is coming from. It was a way in which our people in our past figured this out. Now, as I said when we came up with this same problem last year, there's an easier way. There are alternatives. There are people who have looked at the symmetry and found other solutions. Remember, this solution is still rooted in this function, which is very much us still dealing with the holdover of not really understanding where the electric or magnetic field comes from and trying to come up with a way of calculating magnetic field based on other experiences. Where this was, still based on Coulomb's law, this is strongly based on the force equals QV cross B. Which brings us here to the next analogy. And that analogy is Ampere's law. If the analogy for where the electric field came from Gauss's law, then Ampere's law is to magnetic fields what Gauss's law is to electric fields. Everybody understand?
Yes.
The difference is we can barely use Ampere's law. It's hard to use. But it's, again, a law. Now, I do this because I respect you. Getting a little ahead of myself. Gauss's law. Do you remember all the pieces and why they were structured the way they were? Okay, I want to make sure you do, because the pieces are going to become important. We're going to begin to add to Gauss's law because we're going to be learning something that is, it's an extension of Maxwell's equations. We're going to start to find that these laws had limits, and people have started to extend them beyond their limits. Ampere's law is the same way. You'll notice to be able to calculate Gauss's law successfully, you had to understand that the left side was an accumulation of all charge enclosed within some bounded surface. So you found some three-dimensional shape, you wrapped it around your charge, and you said that if you could enclose a charge and count all the electric field that passed through its enclosure, you could relate the amount of electric field passing through the enclosure with the amount of charge contained within. Follow me so far? That was the whole point. So, Ampere's law is going to have a similar analogy. But to follow that analogy, you understand this is going to have to be about current and not about charge. Right? Something that is dynamic, not static. So instead of having a Gaussian surface, we're going to construct an Amperian loop. We're going to wrap a loop around a current or a group of currents. So start here. And we will therefore have an enclosed current. The amount of current enclosed in the loop. This needs to be a complete loop. It can be of any shape you like, but it must be continuous and bounded. So, again, not a surface, a loop. We're going to conduct a calculation, an integral that is over the entire loop. So it's a bounded integral. If we add up the magnetic field in the direction of the shape and length of our loop over an entire loop, it would equal the amount of current enclosed. Bless you. Now it's similar, but there are differences. There's a constant of proportionality left out here, and I'll point out that that constant of proportionality appears on the other side in this function. And yes, I know, I get it. One more thing just to be different. So, of course, I need to... Well, I'm so glad. For weeks about being more patient as people come to me with problems. I'm trying. This is Ampere's law. It's incomplete, just like Gauss's law is incomplete, but it does the same kinds of things. What we will have to do is come up with what we feel are an appropriate loop, that we can use the symmetry of the loop in order to determine the amount of enclosed current. But the point of this is to be able to use a symmetry or some kind of symmetry to tease out the magnetic field from this to get an expression for magnetic field for specific types of current geometries. Now, please pay attention to the points here. This is not flux, even though he used the word flux. This is not. This is a line integral. And more importantly, it's a dot product with the line integral. We are integrating a length. ds is a length. If our Amperian loop is circular, then our length is going to be a circumference. However, there's a dot product here. The only parts of the magnetic field that contribute to this integral are parts of the magnetic field that are in the direction of the length you are integrating. That's why it's a dot product, and therefore we recognize that we have two vectors here. The direction of the magnetic field and the direction in which you are integrating, the ds. Luckily for you, we'll use this in only 3 possible arrangements, because you have to have a perfectly aligned loop in a situation in which the dot product makes sense. For example, if I have, let's say that this current is, this circle with an X in it, is a long straight wire. Okay? That is passing into the board. So a picture of it, I said straight wire. I'm saying that on purpose. So straight wire. I know from our prior conversations that we are aware that magnetic fields are circular. It is not a huge, it's not a huge stretch to remind you from what we talked about yesterday and the day before that there will be, and that's not particularly symmetric, but I'm running out of time. There will be a magnetic field around this current carrying wire that will be in that direction. I'm using my right hand rule, grabbing the wire and recognizing that using the right hand rule, this should be the direction of the magnetic field around my current carrying wire. Right? We've talked about that right hand rule. If this is the current passing through this wire this way, this is the same wire, then we're talking about a circular magnetic field this way. We also know that magnetic field extends out into space and gets weaker as we get further away. These are all things that we've kind of talked about. If I want to use Ampere's law to figure out the size of the magnetic field, as opposed to what we could place an Amperian loop concentric with the circle, we could recognize that our ds, small piece of length in perhaps this direction, would have a ds that is tangent to that circle. Good so far? Following my argument? That would suggest that this side would be somewhat easy to consider. Since we know that magnetic fields are circular and centered around the current carrying wire, the magnetic field should be the same value for every ds in this circle. And since the magnetic field is circular, it is in the direction of the tangents at every single point of the ds's around the circle, meaning this will reduce to b times ds times the cosine of 0 degrees. Yes. So if I factor out the b, because it's the same for all of them, then I need to integrate the length of one circular loop. That'd be going from 0 to 2 pi r, if I assume that this is r, the radius of my loop, giving me b times 2 pi r. What's the other side? Well, it would be mu naught times I enclosed. The I enclosed would just be the current passing through this wire. Solving this for b, we get that the magnetic field around a current carrying wire. Now, amazingly, this is a very powerful law in a lot of other ways. For example, I have a current meter at home that instead of having to be inserted into a circuit, you fix it around a wire. It clamps closed and measures the induced magnetic field due to that current and tells you the current that must be passing through the wire. So they're cheap. Buy one on Amazon. It'll tell you current. Now, the nice thing is you don't have to cut your circuit and insert the meter to measure current. The bad news is you're still going to be affecting your circuit using this, but it's far less effective than having to cut up your circuit to measure it. Now, I tried to get to this point. I tried to make this point, but I want to emphasize something here. Ampere's law is of extremely limited use. There's going to be the stupid Ampere law problems where they have 5 currents on a page and they're going to have different loops around them and ask which one has the highest amount of enclosed current, which one has the least amount of enclosed current. You know what I'm talking about, right? The kind of problems we had with Gauss's law where they had a bunch of charges in space and different loops around them to ask you which had the most flux and which has the least amount of flux. The difference is, before you leave, there's no special name for this. We don't call this magnetic flux because it's not a flux. As the line integral goes, there's no special name. Now, we will be talking about magnetic flux very soon, but we're going to finish this unit first.